Okay, so looks like most people are here. So let's begin. So from the problem session last week, we talked about virial theorem and the relation between gravitational potential and the density distribution. Okay. Virial theorem. And relation between gravitational potential and the density distribution, which is the very useful Poisson's equation for pi g rho. And this is also just equivalent to the definition of the gravitational potential, which is negative something like the radius and g rho of x prime and dv, right? Yeah, so these two equations are equivalent. And so this is for last week. And this week, we're going to use this again, but a more complete picture for this is that if we assume a density distribution, so if we have a rho density distribution, then we can calculate the gravitational force. Gravitational force, and then with gravitational force, since we know that F is related to gravitational potential by this relation, so we can get the gravitational potential phi, right? And then with gravitational potential, we can further derive the potential energy, right? So potential energy is, like for a system of particle, it would be 1/2 the sum of the masses and their gravitational potential, let's say at Ri. Okay. So let's write it more clearly. This is gravitational potential, and this is gravitational potential energy. All right, so today I will show you this whole process using the most simple density distribution, a uniform density sphere. And in the homework problem, you'll need to do this with a slightly complicated density distribution, but the whole concept is the same. Okay. So for a uniform density sphere, so for uniform density, it means that we have rho of r equal constant. Let's say it's just let it be rho. So this is a constant at a certain, within a certain radius, let's say radius of a. And if r is greater than a, then it should be 0. Okay, so let's illustrate this a bit. So we have a sphere. We have a sphere with a density equal constant, and this sphere has a radius, certain radius of a, and we are interested in the gravitational force potential and whatever experience for any particle experience in this sphere. So let's say we are interested in a particle here somewhere at a radius r, so that we can derive the distribution of those functions with respect to r. Okay, so what we will do is derive the, since this is a sphere and it is like spherical symmetric, so the force is only in the radial direction, radial force. Okay, we will derive this, and the potential is phi of r, and then the potential energy. Okay. Oh, and so, I forgot to mention, so once we have the potential energy, we can use this and apply the virial theorem, right? So this is the whole process. Okay, and then we will apply virial theorem 2 times kinetic plus, maybe I should write it like 2 times the kinetic energy plus the potential energy is 0. Okay, so first step, we will calculate the radial force. So in this case, this is really simple. So we know it's simply just g m over r squared, right? And so we know that from the Newton's shell theorem, at the blue point here, at a point in the shell, it should experience no gravitational force, right? So in this case, when we are calculating the force, we only need to consider the mass inside the interested radius. All right, so this means that the large m can be represented as from 0 to r, the integration, and rho times 4 pi r squared dr, right? So this is the mass within the radius r. Okay, and since now we're considering uniform density sphere, so the mass, like we actually don't need to do the integration, and we know that the mass should be 4/3 pi r cubed times the density rho, right? Since now rho is the constant, it will be just, the mass is just rho times the volume, 4/3 pi r cubed. And okay, so now we can cancel out the r and left with 1 r and get negative 4 pi g m rho over 3 r. Okay. Okay, this is the force. And then next step, we will derive the gravitational potential. So for phi of r, we know, so I just mentioned that based on Newton's shell theorem, the gravitational force experienced from a shell outside the point should be 0. And that means the gravitational potential from the outside part should be a constant. And from the inside part, we can just treat it as the total mass is concentrated at the central point. So this will give us the equation. The gravitational potential is Gm within the radius over r. This comes from the central part, like inside the radius, and also 4 pi g, like the integration from r to the part outside the point r, and integrate with the density. Yeah. So okay, this part is from outside r, and this part is from inside the interested radius. Okay, so with this equation, we can derive that. That would be, we can take out negative g over r, and we know the mass is simply rho times 4/3 pi r cubed. And for the second part, it's just, since rho is constant in our case, we can take out rho. So it's 4 pi g rho. And then inside the integral left with r dr. And so that's just 1/2 r squared, where we plug in a squared and r squared. Okay, so that reduced to negative 4/3 pi g rho r squared. Yeah, because we cancel out this one, and minus, we can also cancel out this 2 pi g rho a squared minus r squared. And let's organize a bit. So we can take out negative 2 pi g rho, and the first term will be left with 2/3 r squared, and then plus a squared minus r squared. Yes, and so this is just negative 2 pi g rho a squared minus r squared. Okay, so any questions so far? So if there's no question, I will move on to calculate the potential. Okay, I see a question. How did 2/3 minus 1 become 1? Oh, yeah, so sorry, I missed a factor here. So 2/3 minus 1 should be negative 1/3, right? And there's also a 2/3 there. So yeah, I missed a factor of 3. Sorry about that. Okay, any more questions? Okay, then let's move on to calculate the potential energy. So now we already have the gravitational potential, and to calculate the potential energy, so potential energy, as I mentioned, the definition is 1/2 and the summation of the m phi in the system. But for a uniform, like not necessarily uniform, but for a density distribution, for a mass distribution, we can write it in the integral form, which is, in this case, we'll integrate from 0 to a, the radius, and phi of r times rho dv, because rho dv is the mass, right? Okay, so we'll basically just plug in the phi we have into this equation. Okay, so this will give us 1/2 0 to a and negative 2 pi g rho over 3 and a squared minus r squared times, we know dv is 4 pi r squared tr. Okay, and this will give us, let's take out the constant. So if we take out the constant, so basically we can cancel out the 2 over here. So that would be 4/3 negative pi squared rho squared and pi squared rho squared. I missed the row here. Yeah, so there should be a row here. Yep, okay. Pi squared rho squared and g, we can take this out. And then inside the integral, it would be just a squared minus r squared and r squared dr, right? Okay. And that gives, so this can be written as a squared r squared minus r to the 4th. Right. Did I miss something? Okay. Okay, so to integrate this, so a squared r squared is just, so we will have a cubed, not a cubed, a squared is taken out and over r cubed. Sorry, should be this, and plug in r cubed, plugging in with a cubed, right? And the second term will be just 5 and r to the 5th, and we will plugging in the a, so that will just give us a to the 5th. Okay. So so let me know if I did some calculation wrong here. So just feel free to unmute if you see any problems. Okay, so this term here would be a cubed over 3 minus, no, a to the 5th over 3 minus this. So that will give us 15, and 5 minus 3 equals 2. Okay. Okay, so that will give us Okay, I think I did something wrong here. Sorry, let me check. Pi square rho square g. Okay, maybe not. All right, let's just do this. So we will get 45 and 8 pi square rho square g. And that doesn't look like the uniform density potential energy. So so just let me know if you see something weird, like oh, and a to the 5th here. Yeah, I don't think I did anything. With the blue box, the phi a square minus r square over 3. Yeah, you're right. Okay, thanks for noting that. Yeah. Okay, so the potential should be a square minus r square over 3. And how would that change? So, so we shouldn't have a factor of 3 over here. And so instead, the factor should be here. And that will give us, okay, so no more factor of 3 here. Negative 4. And again, this gives us a square r square minus 3, r to the 4th over 3, right? R to the 4th over 3. Right, so this term is now a to the 5th over 15, right? Yeah. So now it looks more accurate. So now we have 5 minus 1 is 4. So in the numerator should be 4 over 15 a to the 5th. Yeah. Yeah, so this should be correct now. Okay, thank you for noting the problem. Okay, so now we have, and we don't have a factor of 3 here. Right. So this is now negative 16 over 15 pi square g rho square a to the 5th. Right? Okay, so now we have the gravitational potential energy, and if we substitute the mass like into this equation, we will get, so we substitute the mass in our case is just the volume times rho. and we substitute this into the potential energy here, then we will get a form with a more familiar in the general form of potential energy, which is in terms of gm squared over r. Okay. So for the uniform density sphere distribution, we have a potential energy of negative 3/5 gm squared over r. And we can compare this with the general form, which includes the eta. So compare with general form. We have the general form of potential energy should be negative gm squared over 2 eta times r, where we know that eta should be some constant approximately equal to 1. Okay, so we compare these two equations, and then we will get for a uniform density sphere, we have 2 eta here is basically 1 over 2 eta equal to 3/5, right? By comparing these two equations. So we can get eta equal 5/6, which is approximately 1. All right. So for uniform density sphere, eta is 5/6. All right. So now we have the potential energy, and the last step would be pretty simple. We will just plug this into the virial equilibrium equation. So we have obtained the potential energy, and we will just use the virial theorem to get mass, the virial mass of this object. So so just plug this in. So 2 times the kinetic energy, and as mentioned last week, the kinetic energy should be 3/2 m, and the velocity dispersion squared, right? So there's a factor of 3 because we assume isotropic motion. So, and what we measure is a radial component. So there's a factor of 3 here, and that should be equal to the potential energy we get. Should be 3/5 gm squared. Gm squared over A. Yeah. So that would simply give us, can cancel out the m here. The virial mass is simply 5a sigma r squared over g. Okay. So this will be a this should be a very familiar form. Like you can see many of this equation in papers. So basically if we are assuming the let's say the interstellar gas core, like a core of interstellar gas or something like that, and if we assume it's a uniform density sphere, then we can derive its virial mass using these equations. Okay, so any question so far? All right, if there's no questions, I will give you some hints on the homework because the process I'm doing, the process I was doing is related to the problem 1 of your homework, but the only difference is that problem 1, we should consider plumber sphere, right? So for plumber sphere, we already see this in the homework for last week. The density distribution is something like this times m over r squared plus ap squared. And the gravitational potential, we also show it in the homework last week, should be negative gm. Yeah, so we basically, last week we just, we discussed about the relation between rho and phi, and we just used the Poisson's equation or its equivalent form, right? So, with the density and gravitational potential as we shown above, we can then derive the potential energy, right? By just plugging in the density distribution and the potential. So this should be pretty straightforward. And for the second problem of your homework, let me see. So I believe the second problem of your homework is related to surface brightness. So we need to convert magnitude per arc second square to something like solar luminosity over parsec square. And this is basically almost exactly the same as what I did in the problem session for week 2, which is the first problem session. So if you are confused about this question, you can just go look the notes of the week 2. Okay, and the final thing I want to say today is, so there's also a problem in your homework asking you to calculate the surface density. So something like this. But basically, we assume that the spectral type don't change anything. I mean, for your homework problem. So you actually don't need to just ignore the S here. So the surface density is can be calculated as the integral of rho of r times dz. And just want to recap that this the surface density equation comes from like okay, so like we have a sphere over here, and this is our line of sight. So we are observing in this direction, z. So if we have let's say the radius is r here. Okay, so that's why the surface density is the density distribution at r and integrated along the line of sight. So make sure you remember this when you do the homework. All right, that's all for today's problem session. So any questions?
Yeah. In fact, I have the notes of week 2. I'm still stuck on the problem 2. I don't know why, but I'm really stuck into it, and I really don't know. I mean, I think I understand the problem, but the equations, I don't find the solution with the equations. I mean, maybe I don't use the right, but
So did you fully understand the note for week 2?
I understand the parsec square. So basically, from and the conversion between one radian, or the angle when you see a star like in a plane, and the conversion when you see like a whole surface. So the from radian to steradian, I understand that, but I don't really understand why we have like the 15. I don't know how to convert the I don't know which distance I have to take for the exercise.
Right. Which distance? Okay. So basically now, your problem should be at, you don't know how to convert magnitude to solar luminosity. Is that correct?
Yeah, I think so.
Okay. So, wait, let me open up my note for problem session, just a second. Okay, so do you have my note in hand right now?
Your notes from week 2?
Yeah.
Yeah, I have them.
Okay, so so in week 2, we're basically we're also comparing the magnitude of the sun to the magnitude we desired, which is 25 magnitude, right?
Yeah, okay.
Yeah, and the only difference in the homework problem is that we're comparing one sun, the luminosity of one sun, to 15 magnitude, right?
Yeah, okay. For this problem, right?
Yeah, for a homework problem.
Okay.
Yeah. So if you, I'm not sure if you all know, so the recordings of problem session is actually uploaded. You can find the links in the under the file folder in Canvas. So if you are confused about something and want to go back, you can check the recordings.
Okay. And so, for example, in the week 2 problem session, you took the distance, at 10 megaparsec or 10 parsec. Should I have to take the same distance?
No. You shouldn't assume anything about the distance. And in fact, distance won't influence the answer. So I also showed this in the problem session. So I later changed to 1 megaparsec, and the result for surface brightness is basically the same. Yeah, so actually distance doesn't matter. Like you can just put a D in it and you'll find that it will cancel out. Yeah.
Okay.
Where might be a good resource to find the sun's magnitude in the I band?
The sun's magnitude in I band is table 1.4 showing this? Let me check. Because
it's only magnitude in the V band minus V minus I, right?
Yeah.
You mean table 1.4? So there's no magnitude.
In table 1.4, yeah.
Okay. Let me see if I can. Oh, but table 1.4 gives V minus I, right? Right?
Yes.
Yes. So if you have V minus I, then you can definitely get the magnitude of I band if you have the magnitude in V band, right? That's also what I did in week 2 problem session. So since we are interested in B band at the problem session, and I'm using the V band value and converted it to B band by using the B minus V provided in table 1.4. So similarly, if you have V minus I and the V band magnitude, you should be able to get the I band magnitude. Does
And
that
then
make
it's pretty
sense?
much just following all the same steps.
Yep.
Perfect.